So that is it for me. Are there any last questions? How did I do on time? Not too bad. 5 minutes, okay. So any closing questions? Anything else you'd like to know while I have the stage? So error is very difficult to quantify. Usually our standard practice is we stack up all the worst case things and then hold margin to the stacked worst case. So we look at what's the worst beta angle, what are the worst case properties for alpha and E, what are the maximum dissipations we might have, what are the largest E stars we may do, and we stack all that up, and then we go the other direction, what are all the coldest things, and make sure that that falls within 5C of our design requirements. We usually don't do a lot to try to put uncertainty on it or bound the error for it because we know that there's margin on margin on margin on margin when we stack up worst case of everything. You know, we did a study one time and, you know, we don't spend much of our mission, if any, at a stacked worst case conditions. You know, it just doesn't happen. So the error is kind of hidden in the fact that we've stacked up all the worst case. We expect that that is going to bound any error that the models may have. That said, by the time you get to actual test data, you may find that, okay, well now I want to relax some of all those uncertainties that I have. You know, but then your error goes down when you have actual test data to compare to. It's not, you know, as uncertain. Now the uncertainties are more what's the environment rather than what's the design. The design we have data and knowledge about. So we don't tend to do much, but if you wanted to try to characterize the error, you could say, well, let me do a sensitivity analysis on interface conductances in E stars and see how much that influences things. But usually when we say, okay, we're going to take the worst cases, we're here. If I were to do those sensitivity analyses and come up with reasonable numbers, I'd be coming in from there. So does that answer your question? So for us, we are required to hold 5C of margin. For temperature-controlled components, we're required to hold 30% power margin. But then we test beyond those. So we end up testing to essentially 15C above our expected flight hot or flight cold temperatures. So they test beyond where they expect to be for workmanship, but we carry 5C of design margin and then 10C of qualification margin, if you will, that you hope to never use. So. So the mesh size, again, is going to come down to I need more nodes for thin, low conductivity materials. I need less nodes for thick, high conductivity materials. You know, start with something larger, see what the gradients look like. If I have 10C between two nodes that are coupled together, I probably want more nodes in between there. If I have 2C between it, it's probably good enough. You know, so if you start larger, it's easy to refine the mesh with the refine mesh button and add more nodes. If you start small and find that you've got way too many nodes, well, then you have to manually go back and figure out how to do that. So one of the things I'd like to be able to do with the API is if there's a way that you could say, let me select these elements that are, a contiguous block that don't have other interfaces here, and get rid of that, take these 4 elements and make them into 1 element. Because I have the spatial information that I know where the corners are, so let me see if there's a way to do that, and be able to go from a fine mesh to a coarser mesh with the data. But it would require programming and user intervention to do it. But if I can say, click, 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 these 4, make them 1 element, remove the other 4, then I can go and do that everywhere else, remerge the nodes, and try to go from fine to coarse. Already we have from coarse to fine to be able to do. So, and the other thing I'd love to be able to do is, anytime I have 2 triangular elements, well, let me make them 1 quad element so that I have my diagonal conductor in there. Yes. So by the time you get to actually having flight hardware,
Okay, so
it will go through a testing campaign. So it'll be going through EMI, EMC. It'll be it might be shock tested. It might be acoustics tested. Certainly vibration, and certainly thermal vac. So the thermal test will have 2 parts. It'll be a thermal balance, where we make sure that everything is very stable, so that we can gather the test data. We know our environments. We get all the measured power dissipations. We put all the knowns into our model and see how well it predicts. And if it doesn't predict well, we look and see, well, what areas do we have uncertainty that would get us in the right direction? Maybe the E star that I assumed was too leaky a blanket, and so too much heat came out. Maybe it's better than that. So my test article ran warmer. So my blanket was better than I thought it was. So let me adjust the E star. So that correlation effort, happens after we have the test data, the measured experimental data, and we correlate the model to better predict the performance that we saw in the test with the model. And then that model correlation is used, or that correlated model is used to generate the final flight predictions. It is a mixture of black magic and voodoo.
okay,
So that comes down to the experience of the engineer, how well they know their design, where they think the uncertainties are. It's judgment.
Okay.
There's no push a button and out pops the correct answer. We talked earlier about the solver and whether there was a way to have it do that, and even that just doesn't quite do the job. So really, I haven't found anything that can beat a human in that respect.
Okay.
Yeah, so we try to test or set up our test environment as close as we can to what we expect for flight. We have a saying, test as you fly, fly as you test. So if there's money, we're certainly interested in doing correlations. Usually, by that point, project is over budget, project's behind schedule, and you've done your 30 days commissioning, and everything's working, and everything's within requirements, and they don't care if your predictions were off by 10C. We're way away from limits. So, but other times, it's not working right. Something's wrong. I had one time I got called in to try to understand why Laddie, which was a spacecraft on its way to the moon, was not performing as the thermal model predicted. It was running considerably cooler, and they didn't understand why. So then it was okay, what data do we have from flight? What data do we have from the model? What can we do to try to understand what the environment is in flight? Because it's much harder. I don't have cryo panels and known temperatures around me. I might not have measured powers. I might only have a state flag for something turning on or off. So that becomes a little more difficult to do the correlation. But certainly you would take a look at what you could, budget allowing or there being an identified need because something is anomalous. Yes. So in that case, it's really gathering as much knowledge as you can about the system. So if I'm having to correlate to a flight around the Earth, I need to know, well, what's the beta angle? You know, what time of year are we? Do we have any data for what the solar activity is doing? Do we have any idea, do we have any knowledge of the Earth IR at that point? What's the transient power profile going on? It's really at that point gathering as much data as you can to make inferences about what could be impacting the change. But correlating to transient is difficult. In the end, most of the time, the flight ops, is it within limits? Great. If it's breaking limits, then they're worried about it. But if it's within limits, it's really only the thermal engineer that cares that it's off by 5C. So again, it's knowing your conditions. So, when I make the worst case flight predictions, it's stacked worst case. I'm getting rid of the stacked worst case and saying, what are my known conditions? I know my beta angle now. I know my altitude. I should know my power dissipations. So all those things help to reduce the uncertainty of the configuration of the model such as you can get it. Now, is there a possibility that something broke during launch? Did a blanket tear away or something like that? So that's where you would have to look and see, well, what's the performance versus what I expect? And what areas are far enough out that I think something might be wrong here? So, for example, the hurdles instrument many years ago, didn't behave well because a blanket puffed out and blocked part of their aperture. So, you start off with okay, everything is as I expect it to be, but if you still start to see things that are far enough away and you've exhausted all the reasonable things, now you start looking for, well, what went wrong? What's different than I expected it to be? And, how can I use my model to infer what the impact of this error or this anomaly might be? Does that help? Nothing is necessarily easy to change. I've had times where I looked at the model and said, what was built just cannot answer the question. Let me go look at the hardware again and see what it looks like. And lo and behold, the hardware is very different. Or we didn't include this aspect because we thought it was not important. Well, it turned out to be important. So it really comes down, and every thermal analyst should get out from behind the computer at some point and go look at the hardware. You can build things from CAD all day long, but the real hardware is what goes up into space. Look at the test setup. Certainly before they tear everything down from a thermal vac test, go look at it. Make sure you understand. Look at the GSE. Is it possible that the GSE is what's causing the problem? The ground support equipment. It's really you as an engineer understanding what the hardware is and whether your model reflects the physics of that. Sometimes it's a simple conductor, other times it can be far more complicated. I have to build this bracket. I can't just say it's a 0.1 watt per K. But there is, for correlation, there really is no easy way to do it. The best thing you can do before you correlate is, get as much data as you can. And then the other piece of advice I have is, keep track of every change that you make, and if possible, only make one change at a time, such that you can see what the single impact is of each thing. If you change 4 things at once and it improved or degraded, well, how do you know which of those 4 had the effect? It could be the 3 of them did nothing and one of them was responsible for all of it. So being able to make incremental and step changes is useful. The other thing I made a mistake one time and, started to get my cold data in and started working on correlation, started changing the model, and a week later I got the hot data in, but now I had changed my baseline, so I really didn't know how close I was to the original one with the hot data if I just put in the known values. So, I would say wait until you have both hot and cold or hot and cold in survival, and then start with the correlation of just putting in everything that I know from the test. Don't make any other changes to the model, no adjustments to emissivities or conductivities or E-stars. Just put in, okay, I know all the powers, I know the environmental panel temperatures, I know this heater power, put all the known knowns in and then start working to adjust the model to match. But if you start tweaking too many things before you have enough data, you might be moving off in this direction and then you get the other data and it says, oh no, now you got to come back this way. So when one of them's going that way and the other's going that way, now you got to really figure out, well, what is it that's going to allow that to work? So. And you were worried they wouldn't ask questions. So I'll address that by saying thermal cannot optimize a design, because what might be good for thermal might be horrible for structures or might be terrible for power. So as a design evolves and a design changes, it's really the systems engineering and the systems engineering team that will establish the trade studies of how to improve the design and get everything moving forward towards a better design, rather than, well, this one moved forward, but this one moved back. So thermal cannot operate in a vacuum. Well, in a vacuum on the ground. We have to be able to interface with everybody else, and particularly the systems team needs to be the ones driving optimization. We can help constrain resources or reduce resources locally. I could use less power or do a different radiator, things like that. But how do those changes flow through and have ramifications on other subsystems is very important. And you just can't optimize by yourself. It really is a system that has to be optimized, not the thermal design that has to be optimized. Now, that said, you can look at sensitivities from a thermal perspective. If I made this radiator thinner, this is what would happen. And here's how the power predicts would be different. But whether that is the best thing for the system is really it's for the systems team to decide, not just thermal. Yes. Yeah, if I want isolation, I can make it really, really long and really, really thin. Might break structurally. So it has to be a design that meets everybody's requirements, not just the thermal requirements. Thermal engineers should be good systems engineers. You want to think about the system. It's not just yours, and the more you recognize, in particular, where your subsystem influences somebody else, the better the communication can be. So I know when there's isolation needed for a detector, I know that thermal and mechanical are going to be opposite. I want long, I want thin, I want low conductivity. They want short and fat. So I know that we're going to have to work together to find something that meets both of our requirements. So as a thermal engineer, first person I go talk to is the mechanical person or the structural person when I know that there's going to need to be isolation. So, and the more experience you get, the more you work with other projects and other subsystems, the more you'll start to recognize how thermal fits into the entire system. Yeah. So no, there really isn't anything. It does come down to if you know you're going to have to reduce the model, how far do you have to reduce the model? So, for example, on Roman, we have 150, 200,000 nodes. We have a launch model that's going to constrain us to 10,000 nodes. I don't have a way to take that level of detail and shrink it down to this much lower level of detail. It really almost requires a rebuild of things. Now, that said, there are things you can do if you know that you need to have a much smaller model. You could say, well, let me group together all these things that, I've got, 1,000 nodes here, but the spread of the gradients is only 5 C or 5 Kelvin. So maybe I can only represent that with 10 nodes. But there is no, let me push a button and out pops a reduced model. There are people who are trying to do it, but I think that, much like correlation, is another thing that requires a human in the loop to use judgment to figure out how to best represent in a simplified enough manner while still capturing the physics of the problem. So node correspondence is similar to what you were saying. Let me take these 1,000 nodes and I'll represent them as 100 nodes or 10 nodes instead. So you're just collapsing multiple nodes into one. But even if you did the no correspondence, you still have to figure out what are the conductive couplings now between the nodes that remain, which is a challenge to do.
I see.
Never tried to do that. I think you'd have some challenges to deal with the licensing issue. I don't know what the security posture would look like for, flight operations. You want them in a fairly safe facility that is firewall protected and things like that. And I also think that again, for the most part, if the satellite in flight is operating within its expected parameters, the only person that cares that the model isn't accurate is the thermal person. So the flight operator is probably not going to want to do it. And if they really had questions or wanted to know how would this perform, they'll come to the thermal engineer to ask them that rather than say, okay, well, give me your model and let me figure out how to run it. So I don't know that we want to burden flight operators with now having to learn another tool and do the job of a thermal engineer, rather than come back to the thermal engineer and say, okay, well, if we went into this orbit or we did this maneuver, what do you expect the performance to be? So it's a training and an expertise issue. I would think that it just wouldn't necessarily be practical to try to marry those two together. You're welcome. I think that finite elements aren't going to be any more difficult to correlate than surfaces or finite difference. The uncertainties that you have, that you deal with correlation, are primarily at interfaces, where I've got a contact conductance, E star values, maybe some uncertainty in optical properties. But usually we're not changing geometry unless the geometry was never modeled in the first place. We're not changing the mesh. You might add some fidelity if it wasn't there before, but I don't think that the geometry is the primary area that we target when we're correlating. I think it's much more interface conductance uncertainty, E star values, possibly radiative behavior for things. So I think that the mesh approach that you have for pre-correlation and post-correlation would remain much the same.
Thank you. And
Other than a situation where, okay, I didn't model this component at all, it's not even there, or I just modeled it as a conductor and I need to add that back in, well, then you're back to, let me build the mesh or build the model to represent this aspect that I didn't have before. So basically, if I understand, how do we get our EOL numbers?
I see.
So I'm in code 545. Right above us is code 546. They are coatings and contamination. And their job, and one of the gold rules we have at Goddard, is that the coatings committee, a group of people who are knowledgeable about how coatings degrade, how they perform, will specify for the thermal team what the acceptable values of properties to use for the thermal analysis are. So they take into account, the mission duration, atomic oxygen, the environment, the electron flux, gamma rays, all the things that degrade. And then they give us a report, that's basically, okay, here's the measurement uncertainty, and then here's what we expect the degradation to be, and they provide for us what those values are. Before we get those, it's kind of what did the last project I used have? So that's kind of I pull what I had before until I have better information.
Thank you.
So unfortunately, I can't tell you how they do their black magic, but I do know that there is a group of engineers dedicated to determining what those properties need to be. If it's a new coating, they may do some measurements for it. And then they have, other facilities at other NASA centers where they can do, the accelerated life testing and exposure and things like that. So,
Thank you.
but yes, it is difficult to get those properties. Not sure I followed your question. Could you try it again? If I understand, so you have one part of a model that you believe is good and doesn't ever need to change. And then you have another part of the model of the whole system that is newer and may have some uncertainty and things like that. So what you would try to do is not have symbols and parameters that were part of the good known model being used in the new model, such that I can now make changes to things over here and it only affects this part. So for example, let's say that I had two conductive interfaces or two heat transfer coefficients or something like that. I might say, all right, let me start with the good model. I'm going to name all of the parts here, and now I'm going to make copies of those symbols, but I'm going to put a prefix in front of it that says new. And so now I know that all the new ones are the ones that I want to deal with. I might say new in front of all the submodels. So you can separate out via naming conventions for optical properties, thermophysical properties, symbols. You can group the symbols together on a separate tab so that this group is new and this group is old. So, but it takes a little bit of time for you to set that up to say, don't change this part. But you certainly want to separate out the things that shouldn't change from the things that can change. Is that clear? Does that answer? So one thing to note, if you have a symbol that you wish to change the name for, let's say I have 30 symbols. I could select all of those, and if I do rename symbol, it will bring up an option for all of those to do something. So I can either put a prefix in front of them, I can put a suffix at the end, or I can do a search and replace on a particular character. So if you have a group of symbols that you want to rename and put something in front of, you could do that in one swoop. You don't have to rename each one individually. Clear? that's a programmatic decision. I would never suggest removing the thermal balance, or never suggest removing the thermal vacuum portion. You might consider not doing the balance and not doing a correlation if it's the same. But
Yes.
workmanship, it doesn't matter if the designs are the same. They're two different builds. Two different people or groups of people built it. You have to make sure that the design was built correctly and works. So I can't ever see not doing a thermal test. I could see maybe skipping balance if you believe that the design has been qualified and is ready to go. But I would still probably say, if I skipped balance, I would still want to take a look at what was the thermal configuration for thermal vacuum and run my model in that to see that it matches the data, to make sure that there isn't something different between satellite A and satellite B. So, but that is totally a risk posture and a cost savings that the project would have to advocate. As a thermal engineer, I will never want to give up my thermal balance test.
So,
Again, those are decisions made for programmatic reasons, not technical reasons.
I always
I don't
think
think you really can, because you're not selecting an object in the window. You have to have a way to select the things that you want to have something done in the window.
yes.
So in the window, you can't really do that. No, there's not a way to do that. What you'd have to do is select the objects that you don't want there and turn their visibility off.
Thank you.
But you could do it with the API. Actually, pretty easily with the API. Make a selection set and say, turn off everything, and now turn back on this selection set. So, yep. So actually, without the API, you could do that. So there's a select command in AutoCAD. And so you could say, let me select all the things that I want to have. And now they're in a selection set. Now let me turn off everything. And now let me turn back on the previous selection set, which would be the things that you just selected. Three steps, but still possible. I mean, it would be, I've got some parameter that I don't know what its effect is. And I've got some response that I'm curious about. And so let me increase it 10% higher, 10% lower, factor of 1 too higher, factor of 2 lower. And what does that do to the temperature?
Okay.
So I have a baseline. I have if I increase the parameter, this is what happens to the temperature. I decrease the parameter, this is what happens to the temperature. No, I mean, it depends on how complicated you want to go. So,
Okay.
you know, how many parameters you have, how many parameters you're sensitive to, and what level of confidence you have in the value that you're inputting. Now that said, I haven't used it, but there's another tool out there called Veritrek, which is using thermal desktop and training data. And what they do is you give it your model and all the parameters that you have, and it will go through and it will run a bunch of analyses and then fit a Gaussian distribution to that, such that you could then say, all right, let me slide and play with all the different things, and it will, in seconds, give you what the response of that is. It's a good tool, but I find that for the most part, it gives me the answers I already know. My radiator is too small. I need more heater power. The answers it gives tend to be more on the obvious side. But it is a tool that's out there, and it uses Thermal Desktop. It interfaces with it through the OpenTD API and works. So if you're ever interested in that, you could check it out. The gentleman's name is Derek Engevald. He's in charge of it, so he appears at ISIS pretty much yearly. So, so that would be a tool that you could potentially use for sensitivity analyses. I know they have some case studies, the Mars helicopter, I think the SNC Dream Chaser and things. So there have been some organizations that have tried to use that for sensitivity studies as well, which does more than just say, well, let me make it higher and let me make it lower and only one parameter. It tries to do a little more smarts. You're welcome. So it is, they haven't set the exact date yet, but it will probably be August. Probably late August. They usually have it before school starts. So it tends to be second, third week of August is usually when it is. But right now, we're having to go through, talk with the hotels, conference centers, and see who's available and try to fit it into the small budget that we have from the NESC. So those discussions are ongoing. But when I know the date, I will certainly communicate it to Shinichi-san to let everyone else know.
Yeah, thank you so much for such a long lecture.
Yes, you're welcome.
Let's show our appreciation with applause. Thank you. Thank you so much.